You ever stop and wonder what's really going on inside your calculator? You hit a button like sine or e to the x, and boom, there's the answer. Well, it turns out the secret behind it is way, way cooler than you probably think. I mean, it really does feel like magic, right? You punch in some random number, hit a button for a super complex function, and instantly you get this super precise answer. So how on earth does it do that? What is the secret sauce?
All right, so here's the first big clue. That little electronic brain in there, at its core, it's actually kind of dumb. It can only do the absolute basics. Add, subtract, multiply, and divide. That's it. It doesn't have some magical curve drawing chip inside. And this is the key. All those fancy functions are really just basic arithmetic in a clever disguise. The calculator is using a beautiful, beautiful math trick to build them from scratch.
See, the secret isn't about knowing the exact answer for every single point on some complicated curve. No way. The real secret is knowing how to build an incredibly good fake, a stand-in for that curve using only simple pieces. It's all about the power of approximation.
Okay, so let's start simple, like really simple. Imagine we've got this function, right? The black curve you see here, and we want to approximate it right around that single point A. What's the absolute easiest thing we could do? Well, we could just draw a straight line that just kisses the curve at that one spot.
And you know what? This straight line is a pretty decent first guess. It actually gets two things perfectly right. It has the same value as the function at point A, and, crucially, it has the exact same slope. But you can see the problem. The second you move even a little bit away from that point, the line and the curve start to drift apart. It's a good start, for sure, but we can do a whole lot better.
So, how do we get our approximation to, hug the real curve a little tighter? Well, we add another piece of the puzzle. We're going to add a new term to our equation. And this new term's job is to match not just the value and the slope, but also the curvature of the function, basically how much it bends at that point. We're literally forcing our fake curve to bend in the exact same way the real one does.
And this, right here, is the core strategy in a nutshell. It's beautiful. We start by matching the value. Check. Then we add a term to match the slope. Check. Then another one to match the curvature. Check. And guess what? We can just keep going. We can add more terms to match the wiggle, the wobble, you name it. Each new piece we add is cooked up from a higher and higher derivative of the function, and with each step, our polynomial approximation becomes an almost perfect clone of the original curve, at least right around that point we care about. So this whole step-by-step process of matching derivatives is not just some neat, intuitive idea. Oh no, it has a name, and it happens to be one of the most powerful tools in all of mathematics. So let's turn this intuition into the master formula. It's called the Taylor series, and what it is a formula for an infinite sum of terms. And here's the crazy part. If you could actually add up all those infinite terms, what you'd get wouldn't just be an approximation, it would be a perfect, flawless representation of the original function, and it's all built from information, the derivatives, at one single point. It's kind of mind-blowing when you think about it. And those coefficients, the little k values in the formula, they tie directly back to that intuition we just built. K0, that's just the function's starting value. K1 is all about the slope, the first derivative. K2 is handled by the curvature, the second derivative. And it just keeps going. Each coefficient basically bottles up a specific piece of the function shape into one simple number. And getting this logic, that's the real key. Like Dr. Haber says here, it's not about just memorizing some formula. It's about really getting the process, how it's built from the ground up. That way of thinking, building something really complex out of simple, understandable pieces, that is an absolute superpower for any scientist or engineer. But, with any great power comes, limitations. And the real genius is knowing how to work around them. Okay, so this Taylor series is just gorgeous, in theory. On paper, it's perfect. But the moment you try to actually program this thing into a real-world calculator, you slam right into some pretty serious problems. So here's reality check number 1. A calculator doesn't have infinite time or infinite memory. It just can't sit there adding up an infinite number of terms. It has to cut the series off. It has to stop somewhere. So the big glaring question becomes, where do you stop? How many terms is good enough to get an answer you can actually trust? And to really see why this is such a thorny problem, let's look at a specific example. This comes from a fantastic paper by Henrik Westermark. Let's ask a simple question.
what happens when we try to calculate the sign of, say, 5?
Oh man, this graph just lays the problem bare. On the vertical axis, you've got the error, how wrong our answer is, and on the horizontal, it's the number of terms from the series we're using. Now, to get the error small enough for a calculator-level precision, we're talking way down around 10 to the minus 16, we need to compute, get this, 17 terms. For the tiny little processor in a calculator, that's an eternity. It's just way, way too slow.
So here's the takeaway. For numbers that aren't super close to 0, like our number 5, the series just converges at a snail's pace. But it gets even worse. You end up having to subtract these massive numbers that are almost identical to each other. It's like, imagine weighing a giant truck, then weighing the same truck with a single feather on it, and then trying to figure out the feather's weight by subtracting the two. All your precision just vanishes. This is a real thing. It's called catastrophic cancellation, and for our calculator, it means it's slow and it's inaccurate. It's a total disaster.
But of course, engineers are smart. They figured out some incredibly clever workarounds for this exact problem. These are what I like to call the pro-gamer moves that make calculator math both lightning fast and ridiculously accurate.
The strategy is a brilliant 1-2 punch. First up, you've got period mapping. We just use the simple fact that sine repeats itself every 2 pi. So we can take any big number and map it down into a nice, small, manageable range. And then second comes argument reduction. And this is where the real magic happens. This is where we shrink the problem before we even start to solve it.
So what exactly is argument reduction? Well, it's a technique to make a big, ugly problem into a tiny, easy one. So instead of trying to calculate sine of x directly, we use a clever math identity to find the answer by first calculating the sine of a much smaller number, like x divided by 3. And we can do this over and over, shrinking the problem down each time, until the number we have to plug into that slow Taylor series is incredibly tiny and super easy to handle.
And right here, this is the big aha moment. On the left, that's our original problem, trying to calculate sine of 5. Remember, it needed 17 terms. Now look at the right. After we use argument reduction to shrink that input all the way down to about 0.06, we get the exact same level of accuracy with just 5 terms. 5. I mean, just look at how fast that error plummets. It's a night and day difference. The gain in efficiency is just massive.
So, the really crucial takeaway is this simple but incredibly powerful idea. Don't just charge head-on at the hard problem. Instead, use a bit of clever math to transform that hard problem into a much easier one. Solve the easy problem, which is fast, and then just transform the answer back. Doing it this way makes the calculation unbelievably faster and way more precise.
And, you know, this whole idea goes way beyond just calculators. This fundamental concept of building up something complex from simple, repeatable parts, or breaking a hard problem down into a bunch of easy ones, you see it absolutely everywhere. It's a cornerstone of physics, engineering, computer graphics, even data science.
So, the next time you pick up a calculator and hit one of those buttons, maybe you'll remember the elegant little dance of approximation and optimization that's happening under the hood. It just goes to show you, hiding behind some of our simplest tools is some of the most powerful and beautiful math you can imagine. And it kind of makes you wonder, doesn't it? What other hidden math is quietly powering everything else in our daily lives?